This is the longest video in the course. You can always stop it halfway through and watch the second half at some other point in time. Now don't worry too much if you don't understand everything that's in the video, because we will be implementing the FFT algorithm, and it's really by that implementation that you get a really good thorough understanding of how it works. In this video we're going to derive something called the Radix 2 decimation in time fast Fourier transform. So this is one of the algorithms that we use in order to speed up the computation of the DFT. So as I mentioned in the last video, the terminology FFT, fast Fourier transform, is a generic term used to encompass algorithms which will make the calculation of the DFT a lot quicker. So what we really want to do is we want to make a computationally efficient algorithm. Now we've seen when we did the DFT that if we had n samples, then we would have n bins in the frequency domain. We would therefore have to do n squared multiplications. Now what we want to do is cut down these multiplications, and that's what we're going to do when we introduce this Radix 2 decimation time FFT. Now this isn't the only FFT, there's other ones that are available to us. For example, the Radix 2 decimation in frequency fast Fourier transform. So let's get started and let's get through this derivation. We've already went through a full derivation of the discrete Fourier transform, which is shown at the bottom here. So what we'll do is we'll go through this again, but we'll go through it in a much simpler format than the previous derivations that we've used, and in the process we'll go over some stuff here that should probably be a bit of revision. So let's start off with the complex plane. We've got the real and the imaginary part of the complex plane, and we know that we can represent a phasor. So this is a phasor here, and also the point in pink there, that's the actual complex number, so that's going to be a complex number A plus IB, and we know we can represent that in terms of a complex exponential. So we can say this distance here is going to be r, which by Pythagoras is simply going to be the a squared plus the b squared root, and the angle in here is going to be theta, and we know from the identity e to the I theta equals cos theta plus I sin theta that this distance here is going to be our cos theta, and this distance up here is going to be our sin theta, actually I sin theta. So it means that we can represent this line here with the complex frequency re to the I theta. So we can say that z is equal to re to the I theta, or equivalent we can replace the e to the I theta with our cos theta plus I sin theta. So that's equal to r cos theta plus I sin theta. Now from now on we'll just assume this value of r is going to be a value of 1. It doesn't change any of the calculations or any generality of what we're going to be doing over the rest of the video. So the complex exponential e to the I theta maps the real number line onto the complex plane such that it generates a circle, and the blue line here would be a rotating phasor that rotates round about to generate that circle. So we can see here that our z is equal to e to the I theta. Now z is just a complex number, it's the a plus ib. Now let's consider the case where e to the I theta is equal to 1, so in effect the complex number here is just the value 1. So we're looking for a solution to this, so we're looking for the angle theta that ensures that e to the I theta is equal to 1. So we know that when theta is equal to 0, anything to the power of 0 is just a value of 1, so theta equaling 0 is a solution, so in effect that's this little point here. So it means that if the phasor was to rotate round 2 pi radians, that's 360 degrees, then we would go back to this point 1. So it means that another solution would be 2 pi, and then another solution would be 4 pi, 6 pi, 8 pi, etc. So in general, the solution to that would be 2k pi, where k is a natural number, that's 0, 1, 2, 3, 4, 5. So we can start off at this point 1, and we can go around the circle 2 pi, 4 pi, 6 pi, and so on and so forth. But what we can do is we could introduce another factor of n, which is in the bottom line here. So this is going to split the circle into n elements. So for example, if n was a value of 4, it would split the circle into 4 sectors. And if n was 8, it would split into 8 sectors, and 16 would be 16 sectors. So say, for example, our value of n, which again is just a natural number, the same as the value k. So let's say that value is 4. So then we would end up with e to the I 2 pi, and k would start off at 0, so it would be 0 upon 4, and then the value k would go to 1 upon 4, then 2 upon 4, then 3 upon 4. So we can see that each of these is going to be a phasor sitting at a particular position. So this first one here is going to be the phasor which lies along the real axis. The next one along is going to be the phasor which lies along the positive imaginary axis. The next one is a phasor that runs along the real axis which is negative. And finally, one that runs along the imaginary axis which is negative. So we're going to have our phasors here, so you have one here, and then the second one here, the third one along here, and the fourth one coming down in this direction. So these phasors here are our roots of unity. So for example here, if you were to take this e to the I 2 pi upon 4, and then if you were to raise that to a power of 0, 1, 2, 3, 4, 5, 6, 7, so on and so forth, all the natural numbers, then every single one of them would be equivalent to a phasor of length 1, and they would sit on the circle, and in this instance they would just continually repeat. So that one, we go for this one, to that one, to that one, to that one, to this one, and that one, and so on and so forth. So when we create our discrete Fourier transform here, we've got our value of 2 pi, we've got our k, we've got our n, but we also introduce another factor of small n. So that small n is our index for adding each of these up, because what we have here is a sequence of these phasors. But really what we want to do is we want to go from the sequence of these phasors to a series of the phasors. So a series means a summation of them. So we sum them up over this value small n. And of course we'll multiply each of these phasors in turn by the function of time, which is a sample function of time, f of n, and they're summed up from n equals 0 to n minus 1, and it gives us our function of frequency, which is f of k. So that's another simplified way of looking at the discrete Fourier transform. So don't get lost in this. This is just another way of looking at our surface, which is our e to the I omega t, and splitting it along the frequency axis, so making it discrete along the frequency axis, making it discrete along the time axis, and multiplying by our time function f of nt, and then sum up the values to get our function of frequency. So we've seen all that before whenever we did the derivation of the dft. So when we do our dft, we're going to create n squared multiplications, but there's an awful lot of redundancy within those multiplications, so we're going to have a look at that next. So this is a nice little representation that shows you the redundancy of calculations within the DFT. So we're going to start off with our DFT here. So x of n is the time domain and x of k is the frequency domain. We're going to replace the e to the minus I 2 pi with a value of w. So it means then we can write w, and we're going to keep the n here, which is in the bottom, and we're going to have the n in k, which is here. So we're going to have this x of n w nk sub large n. So again, don't get confused with this. This is just our bed of nails that we've seen in the previous video. But the bed of nails, we've actually given the azimuth for each of those nails as well, because obviously those actually sit in a particular direction. So what we have is the k along here, so this is our frequency domain. We've got our n along here, which is our time domain. So in the discrete Fourier transform, our function x of n modulates these at values here, and then we sum up the values with respect to k, so we sum them up in this direction. So this part of the matrix here is our w of nk sub n, and you can see here that we're going to start up in this corner here, so n and k are both 0, and then as we move along here the k remains 0 but the n increases. The n increases, it goes from 0, 1, 2, 3, 4, 5, 6, 7, but in all instances here the k is equal to 0, so that's just the same as e to the power of 0, which is just a value of 1. So if it's just a value of 1, it's just simply the phasor which is running in this direction here. So if I'm drawing down below, it's just this phasor here. Now the next value down for k, we're going to have the value again, n would be 0, and the next value down, the value over k would be 0, 1 would be 2, but the n value would be 0. So all of these again would give us a value e to the 0, which is just a value of 1. And again, that's just this phasor here. And we've shown those phasors running down in this direction here, and they'll go in this direction. Now, the rest of these phasors here, they're all going to change, but they're going to change in this instance here by a value of our pi by 8. So if we just take this one here as an example, we're going to have our value of k, which is 0, 1, so k is going to be 1, and our value of n is small n there is going to be 0, 1, so the n and the k are going to be 1 and 1. So the 1 times 1 gives a value of 1, and the big N is going to be a value of 8. So we're just going to have 2 pi times 1 upon 8, which is 2 pi upon 8, which is pi upon 4. So pi upon 4 is shown here. Now, thing to note here, it's actually e to the minus I 2 pi, so it's actually going in the clockwise direction. So we're going to be starting off at this point here, and we'll be working round our circle in a clockwise direction. So we can see here we're going to move in effect 45 degrees at a time, so that's going to go in this direction, this, and this, okay? So then the next one along will be going at 90 degrees, so we'll be going this way, this is shown here, and then it will go up to 135, so we're going up at 45 degrees or pi by 4 at a time all the way around the circle, and it's going to give you all of these phasors pointing in these directions. So remember, these phasors are just our little pins from our derivation of the DFT, but we've also added the phase angle in here as well. So this here is our omega nk, and this here is our value x of n. So when we multiply these two together, we've got this one times that times this, that times that, and this times that, and so on and so forth, and then we're going to be adding them up to give us our values here along our frequency axis, which is our x0, 1, 2, 3, 4, 5, 6 and 7. So you can see here what I'll talk about when we talked about the redundancy. You can see that all of these are all pointing in the same direction. This one here gets repeated continually here, 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 and if you hunt through you'll see all other repetitions as well. So this one here gets repeated elsewhere, see it's down here, also down here. So there's lots of repetition here. Plus there's simplifications can be made as well, because these are vectors. So a vector pointing in, say for example this direction, is equal to the negative of a vector pointing in this direction. So there are lots of simplifications that we can create in order to ensure that this system here, the matrix, actually reduces to a much smaller value of the matrix, so there's a lot less multiplications that would need to be done in order to generate these values. So there's two different ways we can go about deriving the DFT. We could continue with looking at it in a matrix format here, and we can try reducing this matrix and seeing what we end up with. But the other option is to do the mathematical derivation. So we're going to work through the mathematical derivation because that's the method that you'll tend to see and you'll tend to learn. So before we continue, let's have a little look at the simplifications that we're going to make throughout the rest of the derivation. So we've got the real axis here, we've got an imaginary axis here, so this is our complex plane. Now we can split the circle into 8, so that gives us 8 phasors, and those are given by W8, so that's the sampling number n, which is 8. And this is the phasor number, so that's phasor number 0, 1, 2, 3, 4, 5, 6 and 7, and it continues round like that. If we were only doing a 4-point DFT, then the value for our sample number n would be a value of 4. And these phasors would run 0, 1, 2 and 3, so the blue ones. So it's this one here, this one, and this one. You can see they're separated by 90 degrees or pi by 2. Now finally, if we were doing a 2-point DFT, then the number of samples would be 2, so it would be W and the subscript would be 2, and it would run from W0 to W1, so the 2 in pink here, and of course these would be separated by 180 degrees. So you can see some of the simplifications we have here due to the symmetry here. We could say our W84, which is this one here, is the negative of W80. Also you could say W58 is the negative of W18, W68 is the negative of W28, and W78 is the negative of W38. We could also look at it, we could say that our W08 would be the same as W40, would be the same as W20, and also our W28 would be the same as W41, and our W84 would be the same as W42 and W21, and our W68 would be the same as W43. So it's easy enough to pick out from this diagram the equalities here with our phasors. So let's continue and we'll work through the derivation of the 8-point DFT. So our FFT algorithm is called a Radix 2 decimation in time. So we decimate this DFT in time. That is that we split it into 2 separate samples. One is odd samples and one is even samples. So this here is our DFT equation. So we separate it into the even parts, xe of n, and the odd parts, xo of n. So that's all of the samples are equal to all of the even samples plus all of the odd samples. And you see that's what we have here. We have 8 samples here, that's 0 to 7. And we split this into the even samples. So this one here gives all the even samples 0, 2, 4 and 6. And this one here gives all of the odd samples. So the odd samples run 1, 3, 5 and 7. So in order to write this out mathematically, what we do is we change the script here from an n to another letter. So we change that to a value of m. So m is equal to n upon 2. So this is the decimation in time. But what we'd like to do is change the index here from n to a new index, which would be n upon 2. So that's this axis here decimated in time, so in effect split into 2. So we call the new index m, and we say m is equal to n upon 2 for all values for n is even. So that means in this example here, if we take the even components here, and if we have, say, the value 2 here, then we're going to have the value m is going to equal 2 upon 2, which is 1. So that'll place this here in this position here. And again, if we take the fourth one, it'll be 4 upon 2, which is 2, so it'll place this in that position. And the sixth one will be 6 upon 2, which is 3, we'll place it in that position. So it takes all of these and it shifts them down so that they sit in values 0, 1, 2 and 3. Similarly, with the odd components, we say that the value of m is equal to n minus 1 upon 2. So for example, the value of 3 would go to the value of 3 minus 1, which is 2 upon 2, which is 1. So this point here would shift to here. And the value of 5, say for example, would be 5 minus 1, which is 4 upon 2, which is 2. So this value here would move to our value position 0, 1, 2, so it would move down to here. So it means that we take all of these values here, and again we shift them to the point 0, 1, 2 and 3. And you see that's written out mathematically here, because if we take the DFT here, now it's a sum from the index, which is now m, equals 0, to the value of, it's no longer n, but it's n upon 2 minus 1. And the first lot of samples here, the even lot, would be x of 2m, and this would be w subscript n to the value of 2mk, and the odd parts would then be given by x to the 2m plus 1, m equals 0, to the limit n upon 2 minus 1, and again the omega n here would now be 2m plus 1 times the value of k. So let's have a look in the next slide and we'll see these shifted to the correct position. So what we have here are our even and our odd pulses. So the even pulses run 0, 2, 4 and 6, and those have been shifted to position 0, 1, 2 and 3, and we've got the new index m, and we have our odd pulses which are going to be 1, 3, 5 and 7, and again those have been shifted to position 0, 1, 2 and 3. Now this equation here is just the same as the one in the previous page. I just copied it over so as we can refer to it. So this is just going to be the odd, the even DFT, and this one here is going to be the odd DFT. But we noted as well in a previous slide that we could write the w subscript n with a 2. That's the same as w subscript 1 with n upon 2. Now I'll show you that just in a second as a reminder. So this is what we have here. So we have our w, and let's say for example our n is 8, so w82 is the same as our w41. So that's just like us saying wn2 is the same as wn upon 2, and the 1 is understood. So we can do the same thing with the odd DFT here. The value of 2 will disappear, it'll just become a 1, and the value of n will now be a n upon 2. Also, the value of k can come out, so we'll have a value wkn. So this thing here is nothing other than a DFT on the even components, and this is a DFT on the odd components. So the FFT algorithm that we're interested in is a DFT on the even components plus a DFT on the odd components times this other factor here, which is wk sub n. Now the wk sub n is sometimes called the twiddle factor. So if you like, what this wk sub n does is it slides these values here one position to the left, because if you noted that whenever we generated the 0, 2, 4 and 6, those were sitting with the 0 point initially sitting here, but the 1, 3, 5 and 7, the first point was actually sitting here. So you can see that in a previous page. So you can see this here, the 1, 3, 5 and 7, the 1's actually sitting here, so in effect the twiddle factor shifts everything to the left. So that's a multiplication with a complex exponential, which is equivalent to shifting the function in the time domain. Now the thing to note here is that we've only worked out the FFT for half of the points, that is n upon 2 points. We still need to work it out for the other half. But the DFT and therefore the FFT are symmetric in the frequency domain. So it means that the second half of the points for an even sequence is equal to the first half of the points for the even sequence, and the second half of the points for the odd is equal to the first half of the points for the odd. So it means that we can therefore write that x of k plus n upon 2 equals x even part of k, x odd k plus n upon 2 is equal to x odd part of k. So it means that finally we could write our x of k plus n upon 2. So in this instance here, let's say the k is the first 4 points of a 8-bit FFT, then the xk plus n upon 2, well if n is 8, that's going to be 8 upon 2, which is 4, so that's going to give us the k plus the 4, so that will be the second set of 4 points. So that's going to equal x even part of k plus x odd part of k times the twiddle factor, which is omega n k plus n upon 2. But we can rewrite this k plus n upon 2 is equal to omega n k times e to the minus I 2 pi n upon 2. So the 2's here, 2 here's cancel, and we're just left with e to the minus I pi. So e to the minus I pi is actually minus 1. So that just equals minus omega nk. So it means that the second half here can be written as x even part of k minus omega nk x naught of k. So finally what we can do is write down the FFT algorithm. So we have the first part which we have already derived, and then we have the second part which we've just derived here in this page. So what we want to be able to do is build up this algorithm in Excel. But before we do that, we'll go and look at this algorithm in something called a butterfly diagram. So we usually represent the FFT in this type of diagram here, which is called a butterfly diagram, and you can see that it's called that because these crosses here are meant to look like the wings of a butterfly. So we take our input here, and this part of our input is only the even parts of our original 8-part DFT. So now it's going to be the values x0, 2, 4 and 6 which go into a DFT, and our odd parts 1, 3, 5 and 7 which goes through another DFT. And you can see this is an n upon 2 DFT because originally n was 8, but now the value of n is only 4, so that's an n upon 2 DFT. So we're going to do 2 of these, and it's going to give us our even outputs and our odd outputs at values 0, 1, 2 and 3, 0, 1, 2 and 3. So again, this here is just a simple representation of what we have up here, and you can see our 0, 2, 4 and 6, 1, 3, 5 and 7 which are actually now at position 0, 1, 2 and 3. So we can see that we get our x0 by adding the even part of 0 plus the odd part of 0. But the odd part of 0 also gets multiplied by that twiddle factor, which is a value of 0.8, which is just our equation we see above here. So we've got the even part, and then we've got the odd part multiplied by our 0, and the subscript n is 8. Now the next one here is going to be x1, so x1 is going to be the even part of x1 plus the odd part of x1 multiplied by the twiddle factor w1 subscript 8, and so on and so forth all the way down. So all we're going doing here is just following this little algorithm here, and that's going to give us the final outputs here, which is our frequency domain on this side and our time domain is on this side here. So from this we're able to look and see how this type of decimation by 2 is able to save us some multiplications. Because we started off with our 8-bit DFT, which is going to give us 8 by 8, so it's going to be 64, or equivalent, it's going to be our n squared calculations or n squared multiplications. But in this instance here we've now got an n upon 2 DFT, and there's 2 of them. So instead of having n squared multiplications, we're going to have n upon 2 squared for this one, and we'll have n upon 2 squared for this one. So we're going to have 2 times n upon 2 squared calculations. Now we're also going to have to add up the n multiplications here for each of these here. So each of these values, x of 0, say for example, gets multiplied by this twiddle factor here, and this one gets multiplied by this twiddle factor. So we're going to have those 8 multiplications there as well. So our final value then for our number of multiplications is going to be the n squared upon 2 all squared times 2 plus the n, which simplifies to n squared upon 2 plus n. So our number of multiplications is now decreased from n squared to n squared upon 2 plus n. But what we can do is we can continue on in this process. So in this instance here we took the 8-bit DFT and we simplified it by using 2 4-bit DFTs. But we could take this 4-bit DFT and we could produce 2 2-bit DFTs for this and 2 2-bit DFTs for this one as well. So let's go ahead and we'll do that next. So looking at it graphically, we start off with our 8-bit DFT and we split that into 2 4-bit DFTs, and we just seen that in the previous page. And this gives us our values of our 0, 2, 4 and 6, so this is the even part of this one, and our 1, 3, 5 and 7, which is the odd part of this one. But then we can take this one here and we can split it into 2 2-bit DFTs. So again we take the even parts and then we take the odd parts. So the even parts of this are going to be 0 and 4, and the odd parts are going to be 2 and 6. Similarly we can take the even parts of this here, so the even parts of this here will be 1 and 5, which are here, and the other even part, the odd parts, are going to be 3 and 7, so that's the 3 and 7 here. So you can see how we're building up this value here. So our 0 and 1 now for each of these, so that's 0 position and 1, 0 and 1 for this, 0 and 1 and 0 and 1, are actually the impulses at 0, 4, 2, 6, 1, 5 and 3, 7 of our original 8-bit DFT. And what we have here are the mathematical equations that define our 4 2-bit DFTs. Now we don't need to go through that, but they're there for you to have a little look at, and you can work out why they're in this format. So let's extend our butterfly diagram. We started off with 2 4-bit DFTs, and then we're going to extend that to 4 2-bit DFTs. So on the left hand side we have our time, on the right hand side we have our frequency, and you can see that these are arranged in 0, 4, 2, 6, 1, 5 and 3, 7. So again you can see that from a previous page. So we can see here our 4 2-bits are going to be running 0, 4, 2, 6, 1, 5 and 3, 7, and it runs like that just because we have decimated the 8-bit into 4-bit and shifted, and then decimated the 4-bit into the 2 bits and shifted, and we've done that the same over here. I've also written the FFT algorithm up here on the left hand side for reference, and on the right hand side here I've drawn out the phasors. So again, we've got the phasors in yellow, which are going to be the 8-point DFT, so that's going to run W8 from 0, 1, 2, 3, 4, 5, 6, 7. So we've split the circle into 8 parts, so if you like at 45 degrees or pi by 4. Now equally we can split that into the 4-point DFT, so the 4-point DFT would be W40, and this one down here would be W41 and 42 and W43, and these are written in blue. And finally we can split the DFT, we can do the DFT with only 2 values, and those values are going to be given by W20 and W21, which are just 180 degrees apart, so that's just these 2 lines here. So we're going to use this here in order to read through the rest of this butterfly diagram. So let's start talking our way through some of this butterfly diagram. Now we'll start off with a value of x0. So at this point here, that's going to be according to the algorithm here, the value k is going to be 0, so it's going to be the x even part of k, so the even part is going to come from this point here, which is x0, so it's going to be x0, and that's going to add on to that the value of the odd part, which is going to be this part here, which would be our x4. But the x4 here is going to be multiplied by this wnk. Now to keep it simple, we'll keep n as a factor of 8 in all instances here. So that's going to be 8, but it's going to be the value k, which is 0, so in effect it's going to be this little pink vector here. Okay, so this little pink vector here, although we've written it down as 8, 0 just to get started and we can call them all 8, it is still equivalent to actually W02, which we'll see in the next page. So that's this point here, and we can move down on to the next point here, and again we're going to have for this value here, we're going to have the even part, so the even part is the x0, and then the odd part here is the x4. Again, the x4 is going to be multiplied by wnk. So again, our value for n here is our 8, but this instance here, our k value here is going to be our factor of 1, 0, 1, 2, 3, 4, so it's going to be this one here. So it's going to be this little pink line here. So this is in effect our W84 here, which again, if you were looking at it in terms of the value of our n being 2, this would be equivalent to our W12. But again, we'll see that down below. So all we're going to be doing in this part here is jumping between the 2 pink phasors. So we're going to be jumping between our W08 and our W48, and you can see here, and each of these are all the same. We're going to have our W08 running along here, along here, along here, along here, and we're going to have our W48 running in this direction. So those are all the same. So that's the first part dealt with. So that's us looked at our 4 2-bits. Now what we're going to do is look at our 2 4-bits. So our 2 4-bits are going to be given by the even bits 0, 4, 2 and 6, and the odd bits 1, 5, 3 and 7. So now we're going to have the value of n is equal to 4. So we'll be following the blue phasors here, which are separated by 90 degrees. So these phasors are going to be given by our W08, W28, W48 and W68, and you can see those values here: W08, 28, 48 and 68, 08, 28, 48 and 68. So now we no longer have our even and odd, even and odd, even and odd, even and odd. We actually have our even, even, odd, odd, even, even, and odd, odd. So the two even parts here are going to be given by just the straight through connections, plus the odd parts, which are going to be multiplied by the fiddle factor. And these are the fiddle factors here, which we've seen are W08, 28, 48, and 68. And again, it repeats in the bottom line. So this is the similar setup that we have back here, but it's just doing it for sets of 4 instead of the sets of 2. And finally we have our last section here, which I won't talk through because we've already seen this whenever we looked at the two 4-bit DFTs. So that covers the butterfly diagram there, but as I said, we have assumed all the values of n are equal to 8, but what we can do is we can replace the W08 with the W04 and the W48 with the W24 or the W02 and so on and so forth. So we can replace the actual values here. So rather than having the index here 8 in this section, we could have the index 2 in this section, we could have the index 4 in this section, and the index 8 in this section. So I won't talk you through every single part of that, just let's go and we'll have a look at it in the next slide. So here's the final simplified butterfly diagram here, and you can see that the values of n down this lot here are value of 2, and down this lot are the value of 4, and down this lot the value of 8. You'll also see that some of them have been replaced by -1, and you can see that up here because our W48 or W24 and W12, these here are all got a value of -1. So this is the final simplified version of our butterfly diagram. So let's go and we'll have a look and we'll see mathematically how much an advantage the FFT has over the DFT. So we can continue splitting the DFT until eventually we get down to a value of 1 and we wouldn't be able to split it any further. So for example, we started off with the value n is equal to 8, so we split it into n upon 2 points, and we could split it into 2 n upon 4 points, and after that we can't split it any further. So we could look at, in generality, saying that we started off, we could split something down into n upon 2, n upon 4, and you could have an n upon 8, n upon 16, 32, so on and so forth. So you could have a value of n of over 2 to the power of p, and eventually that would give you a value of 1, and you couldn't split it any further. So therefore you could rewrite this and you could say that the value of p would be equal log to the base 2 of n. So in effect, p is just the number of different splits that you have of your DFT. So for example, if the DFT was a 32-point DFT, then you could split it in 5 different positions. So it'd be 2, 4, 8, 16, and your original would be 32. So it could actually be split 4 times. So we've seen that splitting it once, that is n upon 2, gave us our n upon 2 all squared times 2 plus the value of n, which equals n squared upon 2 plus n. So we derived that in a previous slide. So if we were to take this here and we were to iterate it again, so we'd now split it again into n upon 4, then we would have 2 times. Now it would no longer be the 2 times n upon 2 squared, it would be 2 times the n upon 4 squared, and also it would be plus n upon 2 plus n. So this is just an iteration here, and that's going to give us a value of n squared upon 4 plus 2n. So take your time and put the values in, convince yourself that that's correct. So if we went to a value of n was split into 8, then what we would have is we'd have this here would then be iterated, so it would be 2 times the n upon, now the 4 would now become an 8, and that should actually have a little squared there, plus n upon 4, all plus n upon 2, all plus n. So that whole thing there is going to give us n squared upon 8 plus 3n. So there's a lot of fiddly bits there, but you can check that out and convince yourself that that is the case. So you can see here the process that we're going to be working through. We're going to have n squared upon 2, n squared upon 4, n squared upon 8. So it goes 2, 4 and 8. So that 2, 4 and 8 is nothing other than our value of 2 to the power of p. So in fact in this instance here, p is equal to 1, so that's 2 to the 1, and it's 2 to the 2, and it's 2 to the 3. So this is just going to give us our value of n squared upon 2 to the power of p, and this second term here is just going to be the value of n, 2n, 3n, so it's just going to be the value of pn. So finally we're left here with our n squared upon 2 to the p plus p to the power of n. Now this can be rewritten as n squared upon n plus n log to the base 2 of n. So this thing here then can be approximated to the value n log to the base 2 of n. So we've gone down from an n squared calculation to a calculation of number of multipliers are going to be n log to the base 2 of n. So let's go and we'll have a look finally in the last slide, and we'll see what that means to us and how much calculation time is going to be saved. So let's say we're going to do a DFT, and we're going to sample it at 3 different rates. So let's say the first sampling rate was going to be 1000, the next sampling rate is 10 to the 6, the other one's 10 to the 9. Then the number of multiplications that we would have to do in order to do the straightforward DFT would be the n squared. So that's going to be 10 to the 6 multiplications, that would give us 10 to the 12 multiplications, and that would give us our 10 to the 18 multiplications. So that's just each of these squared. But if we were to use the fast Fourier transform algorithm, then this 10 to the 6 would actually become 10 to the 4. The 10 to the 12 would become 20 times 10 to the 6, and the 10 to the 18 would become 30 times 10 to the 9. Now to put that into perspective, let's say each of the multiplications was to take 1 nanosecond. That would mean that this 10 to the 18, it would be 10 to the 18 nanoseconds, which is approximately equal to 31 years. And this one here would be 30 times 10 to the 9 nanoseconds, which is approximately 30 seconds. So you can see here then that by using the fast Fourier transform, we've taken something that would take 31 years, would now take only 30 seconds. So you can see here the amount of savings that we have by using the fast Fourier transform. So this has been a long and difficult video. I suggest if you're unsure you take your time to go and read it again, or equivalently over the next couple of videos we're going to actually implement the FFT algorithm in a couple of different methods, and that really helps to cement your understanding. So thank you for listening. I'll get you on the next video. Goodbye.